Yes, it's empty the guy. Let's do some summary of some of the important information about penicillins. Remember, this is our structure for penicillin G. This is the structure of penicillin G. But penicillin G, remember, was the first penicillin. It was discovered that it acts mostly on gram-positive bacteria, because this R group is a benzyl group which is highly lipophilic, so cannot easily penetrate the gram negatives. Again, this very penicillin is highly labile to acid because of the availability of these electrons, such that they can form a thiazolidine ring. Then this ring breaks, as we saw the mechanism of acid instability. So it is labile to acid. Again, this very penicillin, it was discovered that it was destroyed by the beta-lactamases. So it was not effective for those bacteria which produce beta-lactamases. So it was destroyed by beta-lactamases. What is destroyed? So they had to modify to get the penicillin which can have these abilities, such that it can act on also gram-positives, it can be stable in acidic state, and it can resist the destruction by beta-lactamases. Now, remember, we talked about this alpha carbon. This is the amide side chain. This is the amide group. This is the alpha carbon, the first carbon to the amide group. To make the acid-resistant penicillins, they modified the alpha carbon. They put an electron withdrawing group. For all those acid-resistant penicillin, they have electron withdrawing group attached to the alpha carbon. So this is the alpha carbon. Let me use red. This is the alpha carbon. So this is the electron withdrawing group attached to the alpha carbon. Why? Because this electron withdrawing group makes these electrons unavailable for formation of this thiazolidine ring. So the acid labile was the problem of being acid labile was removed. Now these penicillins, which have the electron withdrawing groups, makes these electrons unavailable for the other mechanism, meaning that all those penicillins having the electron withdrawing groups, they are stable in acid, so they can be taken orally. So this one, because it is acid labile, it is taken parentally. What is administered parentally. So this structure is the pen V. This is pen V. Then this structure is oxacillin. So chloroxacillin, meaning we have a chlorine here for chloroxacillin. Then dichloroxacillin, we have another chlorine there. For fluoroxacillin, instead of this chlorine, it is a fluoride group. Then for amoxicillin, okay, this is ampicillin. Then for amoxicillin, there is OH. So we modified, or they modified, the structure of the natural penicillin, which is the pen G. This is pen G, or benzyl penicillin. So they modified, meaning that now these penicillins, they are acid stable, can be given orally. But it wasn't not yet, because there is a problem that penicillins, they are easily destructed by the beta-lactamases. These ones, though they are they are acid stable, but they are destroyed by the beta-lactamases. So they are to cater for that. Now, again, at alpha carbon, to make those penicillins to be stable against beta-lactamases, they modified the R group. They made the alpha carbon to be part of the ring structure. Now, this is the alpha carbon, I see. So it is part of the ring structure. This is the alpha carbon, but it is part of the ring structure. So this is the structure of methicillin. Then this one is the naphthalene. Then oxacillin, chloroxacillin, dichloroxacillin, and chloroxacillin. We have seen the structure here. We said for oxacillin, there are no these chlorine groups. Then for chloroxacillin, there is one chlorine at the ortho position. Then for dichloroxacillin is this one. For fluoxacillin, this chlorine at the ortho position also, this one was substituted with fluoride group. So meaning that these penicillins are beta-lactamase resistant, cannot be destroyed by the beta-lactamases. So meaning addition of these methyl groups, addition of these other groups, they increase the bulk of the penicillin. So meaning that these penicillins, though they are beta-lactamase resistant, and some, as we saw, like these ones, they are also acid stable. They are acid stable, but they are not extended spectrum. They don't have extended spectrum because they act on gram positives. Why? These chains or these groups, they are highly lipophilic. These groups are highly lipophilic, so they are not easily penetrating the membrane of the gram-negative bacteria. Meaning that these ones, they can target those bacteria which are beta-lactamase producing bacteria, but which are gram positive. An example is Pseudomonas aeruginosa. The Pseudomonas, the Staphylococcus aureus, they target this bacteria which is beta-lactamase producing gram positive. It is a Staphylococcus aureus. So these ones, they can target this bacteria. Then for extended spectrum, those penicillins which can act on both gram positives and gram negatives, meaning that we have to retain the hydrophobic part for gram positives, but making it more polar such that it can also penetrate the membrane of the gram negative bacteria. So if we say that we are increasing the hydrophilicity, it doesn't mean that penicillin is completely hydrophilic. So we are increasing the hydrophilicity that it can penetrate the gram-negative bacteria, but they also retain the activity against gram-positive. Now, for extended spectrum penicillins, at the alpha carbon, they put a polar or ionizable group. An example, ampicillin, there is a polar group, which is amino group here. Amoxicillin, there is amine and OH. So these ones, ampicillin, they are extended spectrum. Then cyclacin, it also has the amine group at the alpha carbon. So meaning ampicillin and the amoxicillin, they are acid resistant, and again they are broad spectrum. They are broad spectrum. So these ones, they can be given orally. They can be given orally, and they are extended spectrum. Now, when it comes to carboxypenicillin, for example, ticacillin, it has a carboxyl group here, though its structure here, it's a heterocyclic. For carboxylin, it has a benzyl group, then it has a carboxyl group instead of the amino group. So meaning that this carboxyl group or the carboxyl group is a polar group and it can be ionized. So these ones, they can also penetrate the membrane of the gram-negative bacteria. But for carboxypenicillin, they can target bacteria like Pseudomonas aeruginosa, but they are not as good as iridopenicillins. Now, iridopenicillins, I have an example here. This example is azirocillin. This azirocillin has this structure. So this part is relatively polar. It can penetrate the gram-negative membrane, and when it reaches the periplasmic space, it can form or it can interact with the receptors there, such that the moment it enters, it is very hard to pump it out, because we know some gram-negative bacteria can pump out the penicillins. That's one way or one of the mechanisms of those resistant bacteria. Also, since these penicillins are extended spectrum, but they are destroyed by beta-lactamases. So most of the time, these penicillins are given with beta-lactamase inhibitors, because for them, they are destroyed by beta-lactamases by the extended spectrum. So to reduce on their destruction, they are given in fixed doses with beta-lactamases. For example, ampicillin. Ampicillin is there with ampicillin with sulbactam. It's there with sulbactam. Then amoxicillin is there with clavulanic acid. You find piperacin, for example, piperacin with tazobactam. Then you find ticagrelin with clavulanic acid. You find them in fixed doses. Then ticagrelin and clavulanic acid, it is marketed as timentin. Then piperacin and tazobactam is marketed as zosine. Then amoxicillin and clavulanic acid is marketed as augmentin. Then sulbactam and ampicillin, please, that one will be answered in the comments. Thank you guys. Thanks for watching. Please subscribe, follow, like, and comment. That question, please, in a comment, I think it will be answered. Thank you for watching.